In this video, we're going to begin our discussion of the reaction previously mentioned, and we're going to discuss the mechanism of substitution reactions, and mechanism we abbreviate as MXN. This is going to be the first part of this two-part video that is going to be discussing the reaction of ROH plus HX goes to Rx plus H2O. So this is the reaction we're going to be examining in the next two videos. So what is a mechanism? So again, mechanism abbreviated as MXN. So mechanisms are showing the steps. So it shows the steps by which reactants are converted into products. It is not necessarily entirely correct. It's our best guess. Often we can't examine these steps on a small scale basis, and we're just doing either supported by calculations or supported by knowledge of similar reactions. So this is going to be a best guess as to how reactions are occurring. And we call each step in the mechanism, we call this an elementary step. Elementary step meaning that they're not necessarily products or reactants, but they are intermediates in a reaction. It is each individual step combined is going to make this overall reaction that we see here. And there may be many steps in between what we call reactants and what we call products. There may be many different transitions or intermediates that occur to go from one point to the next, but we do see each of these combined in elementary steps. We do see the overall reaction of ROH plus HX goes to RX plus H2O. So the first type of reaction we're going to examine is called an SN1 reaction. So an SN1, and we'll talk about this more in the next chapter. This is N for nucleophilic, meaning it includes a nucleophile. Substitution, S for substitution. And 1 meaning unimolecular. 1 for uni. So this is a nucleophilic substitution in a way that is unimolecular in character. So an example of an SN1 mechanism would be, say we take T-butanol and we add HCl, and we would convert it into T-butyl chloride plus H2O. Now these SN1 reactions are going to be on secondary or tertiary alcohols. We'll see that later in the video that primary and methyl alcohols are going to proceed in a different type of mechanism, similar but different. We'll see that these secondary and tertiary alcohols will proceed via an SN1 mechanism. So let's look at this step by step. So there's going to be 3 steps total in an SN1 mechanism. Each are going to be elementary steps, and combined we will see that they add up to make this total reaction we see above. So what is step 1? So step 1 is going to be protonation of the alcohol. So we have our alcohol plus HCl. And I'm going to draw the reaction arrow. So mechanisms are often drawn with arrows. We always go from areas of electron density to areas that are electron deficient, meaning we're going from nucleophile to electrophile. In this case, we have an O that has electrons, and we're going to draw it to the H, which is electron deficient. Remember, if we draw these, this would be delta positive and this would be delta negative. So we have a negative charge attracted to a positive charge. We push these electrons onto the Cl. And we have effectively protonated the alcohol. So this goes from OH to OH2. This is going to have a positive charge now. And we would have a Cl minus counter ion that is left as a result of this protonation. Now, things to note, we have this would be our base. This would be our acid. So as we see, this is going to be an acid-base reaction. And as we know, acid-base reactions are going to be very fast. So this is a fast step in the process. We also see that since we have 2 reactants that are involved in the process, we call this bimolecular. Bimolecular meaning that there's two reactants that are involved in the process. So this is a very fast process. We have the base and the acid. This particular intermediate here with a protonated oxygen, we call this an oxonium ion. And if it's attached to an alkyl group, we call this an alkyl oxonium ion. So this protonation of the alcohol generates an alkyl oxonium ion and a counter ion to balance out the charge. So that is the first step of this mechanism. It's very fast. It's an acid-base reaction. I guess what I should note is since this is an acid-base reaction, this is an equilibrium. So depending on the strength of this acid, we would either push it forward or push it backwards. This is why HF is not particularly effective in a reaction like this. For instance, HF in this case would be too weak of an acid to protonate. In fact, we would see the reaction go backwards. HCl, HBr, and HI are all strong enough acids to push this reaction forward and get it to the next stage of the mechanism. So let's look at step 2 in the mechanism. So step 2, we start with our alkyl oxonium ion. We have a plus charge on that O, and we call this step, this is the dissociation of water to form a carbocation. And a carbocation is simply a carbon with a positive charge on it. So the way we would push arrows for this is we're going to take the electrons in this bond and we're going to push it onto the oxygen, effectively breaking this bond. And what we'll be left with is we'll have a carbon with a positive charge on it. Remember, we've broken this bond, so now that carbon that the H2O is attached to is now electron deficient. And we'll be left with H2O, which has left now. Now, this, as we see, there is only one reactant here, so we would call this unimolecular. And this is where the SN1 reaction gets its name. This is unimolecular, and since this generates a carbocation, this is our slow step. This is going to be the slowest step in the reaction. This is going to really designate how the reaction proceeds. And we'll see in the next video the argument for how fast this reaction can go. Just to note, this carbon, this carbocation is sp2 hybridized. What we see is we have a planar tri-substituted carbon with a perpendicular empty p orbital. That's the carbocation. And we'll see that there's going to be interaction of this carbocation with a negative charge in the next step. So it goes from this sp2 hybridized intermediate. We would call this an intermediate because it is going to be used up in the next step. We would call this alkyl oxonium ion also an intermediate because it is used up, is generated and immediately used up. And we're going to generate an equivalent of water here. So the final step in this reaction mechanism, step 3, is going to be the recombination, I'll just say recombination of X minus with the carbocation. So what that looks like is we now have our carbocation. We have a Cl minus. This is simply physics. This is negative and positive charges attracting. We see the Cl minus be attracted to the positive charge. And what we're left with is, if you were tracking along, we started with the alcohol and we're now left with the alkyl halide. If we're going from nucleophile to electrophile, this would be our nucleophile, this would be our electrophile. We always draw our arrows from nucleophile to electrophile and we're left with the alkyl chloride at the end. Since this is simply a neutralization of charge, this is going to be fast. And it's based on electrostatics. So this is purely a physics problem. It's simply they need to be close to one another and they recombine to form the alkyl chloride. So this is going to work for secondary and tertiary alcohols, but let's examine the mechanism of reaction for primary and methyl alcohols. So primary and methyl alcohols, so what we saw is secondary and tertiary are going to be SN1. Methyl and primary are going to be SN2, SN meaning substitution, nucleophilic, and then 2 standing for bimolecular. As you can imagine, bimolecular means that there's going to be 2 reactants involved in the particular mechanism. So an example of this reaction would be, you have ethanol plus HBr, and we go to the ethyl bromide plus H2O. So let's examine the mechanism by which this would happen. Now, the first step of this problem is going to be exactly the same. So this is protonation. In general, in mechanisms, if you have acids and bases near one another, they are going to react. And in this case, we have an acid and a base near one another, so it is going to react. So we have an OH, we have a nucleophile attacking an electrophile. It's going to push those arrows. And what we're left with is the alkyloxonium ion, which I'll abbreviate as OH2 plus Br minus. Again, this is very fast since it's just acid-base. And it is going to result, see if I label here, we have the base, we have the acid, and we have the conjugate acid, we have the conjugate base. Again, this is driven forward if the HBr is stronger than the conjugate acid. In this case, HBr is stronger than the conjugate acid, so this reaction is pushed forward. Again, this would be an equilibrium arrow, but we would strongly favor the products in this case. Now, SN2 reactions are only 2 steps. So we saw SN1 reactions are 3 steps, SN2 reactions are 2 steps. So let's look at step 2. Let me make that black. So we have step 2 for our SN2 reaction. And this is going to be, instead of dissociation of H2O, our step 2 in the SN2 reaction is going to be nucleophilic attack. So what we have is we have our OH2 plus, our alkyloxonium ion hanging around. We also generated a Br minus, which is now a good nucleophile. And what we're going to have is this nucleophile is going to attack and push out H2O. So we have formed one bond here, and we've broken another bond there. And as a result, we've formed a new CBr bond, and we've lost H2O. H2O in this case, we call this this is what we mentioned is called a leaving group. H2O is a good leaving group, and we see that OH is not a good leaving group, but H2O is stable as it leaves, so we call it a good leaving group. This is our slow step. It is bimolecular. And we break and form a bond at the same time. So it all happens in one step. Since it happens in one step, we call this concerted. So we call this bond breaking and forming a concerted mechanism. Now, this can't happen on secondary and tertiary alcohols because of steric reasons. So if we look, say we have OH2 versus a tertiary alcohol, and we're using the same nucleophile, Br minus. If we look at this primary alcohol, we have nothing blocking our way to come in and push out this OH2 plus. We have nothing blocking right here to prevent us from coming in. However, if we try and come here, we've got 1, 2, 3 carbon groups that are taking up a lot of steric space. We call this steric bulk. So this is taking up so much space that this is not going to happen. So that's why instead we have the OH2 dissociate first and make a carbocation. And there's another reason that this happens as well that we'll discuss in the next video, but this is one of the reasons. It's the steric bulk that prevents the halide anion from coming in and doing what we call a backside attack. So this is called backside attack because it's coming from behind the OH2. We can't physically do it because we've got so much steric bulk here blocking us from doing that. You'll also notice here that there's no carbocation intermediate, and that's a key distinction between SN1 and SN2 reactions, is that in an SN2 mechanism, there's no carbocation formed in the process.